Good morning, everyone. Welcome back. So we're going to finish up with the last couple of examples on the section 13.4, which was on space curves. And the idea here was we were thinking of it as an actual particle traveling along the curve. And so we could assign things like what a velocity is, and therefore the rate of change of velocity is acceleration. And what we ended up with at the very end of last lecture was this idea that in space, acceleration can sort of come in two components. You think of this as sort of the two varieties of acceleration. Acceleration could come as a result of the actual speed of the object is changing, or the acceleration could come as a fact of the direction, in some sense, the direction of the object is changing. So remember that velocity is a vector, and so it has both a magnitude and a direction. Acceleration is the rate of change of the velocity. And so we're looking at the acceleration as its two components, the rate of change of the magnitude of the velocity vector, which is sort of the rate of change in speed, and also the rate of change in the direction of the velocity vector, which is what we call this normal acceleration. So to briefly summarize, acceleration can be decomposed into two components. Whereas if you think about it, velocity is only acting along one of these directions. Velocity is a vector that points in the direction of the unit tangent to the curve. So velocity is always tangential to the curve. And now we're seeing that when we take this derivative, we can also get this extra component that's normal to the curve as well. And so that's what we ended up with last day. So we started with the idea that, okay, if we're going to want to compute, oops, I've lost my pen here. Just 1 second to get this pen active. Let's see if this works now. Yeah, it's working now. So I'll plug back in. And hopefully we'll come up immediately here. There we go. So we start with what our velocity vector is. Our velocity vector is the magnitude times the unit tangent vector. And then we differentiated that. And when we differentiate it, we use the product rule, scalar times a vector value function. And that gave us the next line. And then we just noticed that we can work out what t prime is. It's related to curvature. So we used our curvature result. That said, the curvature of a space curve is given by the rate of change of its unit tangent vector with respect to t divided by the rate of change of the vector function r. And so that gave us these two components of acceleration. The interesting thing to note here, when you look at this, it's a formula. At the end of the day, we've got this formula that tells us what the acceleration is. But what we should be able to do is look at this and say a little bit more about what this formula is telling us. So the two key points here are that the formula has a component that's in the tangential direction and a component that's in the normal direction. The tangential direction, the acceleration we get there is because our speed is changing. It's because we're either speeding up or slowing down. Whereas in the normal direction, it's because our direction is changing. That's our curvature. The magnitude of our acceleration in our normal direction not only depends on how the curve is bending, its curvature, how big or small the curvature is, but it also depends on how fast we're going. So you can think about it, if you're driving in a car down a highway, if you're going in a straight line, the acceleration you feel is because you're changing speed. But if you're going around a curve, you could maintain a constant velocity, I shouldn't say velocity, a constant speed, because that's what your speedometer is measuring. So you can maintain a constant speed. Say you're on the highway and you're driving 80 kilometers per hour, but you're going around a curve, you are accelerating because your velocity vector is changing. The magnitude isn't changing, so you don't have an acceleration in the tangential direction. What you are experiencing or what you're feeling is an acceleration in the normal direction. And that acceleration in the normal direction is because of how sharp that curve is or how mellow that curve is. In some sense, it depends on the radius of the curvature. So what we call, if we try to fit a circle that sort of matches that curve, that would be the radius of the corresponding circle, and that's 1 over the curvature. So the radius of curvature is 1 over kappa. So if you have a really big, a high curvature, it means you're like traveling along a circle of a really small radius. So you're curving or you're turning really rapidly. But if your curvature is really low, it means you're traveling around a circle essentially of a really large radius. So it's a very mellow curve. So the thing you're experiencing when you drive down a highway and you go around a curve is the acceleration is due to the curvature, how high that is, how fast you're turning. But it also depends on your speed as well. In fact, it's as it's shown here, it depends on the square of your speed. So if you go around a corner at, say, 40 kilometers per hour, but then you take that same corner at twice the speed, this is so 80 kilometers per hour, the acceleration in the normal direction is basically proportional to the square of that. So we're going to feel 4 times as much acceleration if we double our speed going around a corner. So that's, you might have noticed this if you've driven a car or you've been a passenger in a car or a bus, that even slight increments in speed as you go around corners, you feel the acceleration a lot more. So you feel those sort of centrifugal forces, if you will, a little bit more. Just with small increments in speed, and that's because it's proportional to the square. So that's what this formula is telling us. It's telling us how our acceleration is going to depend on our speed and the curvature of the curve we're going around. So let's go ahead and see how we can calculate these things. So I'll just keep that up. The acceleration is the 2 components. So our rate of change in our speed and our rate of change in our speed and our direction, our component in the normal direction. The way we can compute both of these is as follows. That's how we can compute the tangential component of acceleration, and that's how I can compute the normal component. What I find really cool about this is that these formulas are virtually identical, with the exception that there's a dot product in one and a cross product in the other. And this shows sort of the deeper nature about dot products and cross products and how they're sort of fundamental in the geometry of 3-dimensional space and how closely related are. They seem to be completely unrelated when we first introduced them. The dot product was we multiplied all the components together and added them up, whereas the cross product was this funny way of mixing components together and forming a new vector. But a formula like this shows that they are really intimately connected. Cross products and dot products are really intimately connected to one another. So let's see how we can actually get these results. I'm just looking at the formula here. Yeah, so you got it, James. You're making the connection with the radius of curvature. So if the curvature of the curve is k or kappa, then what we call the radius of curvature is 1 over kappa. How did velocity get squared in the second term? Good observation. Let's see. So there was one velocity that came about from doing the product rule on this velocity function. So we got our vector value function, which I've circled here. I've done it in pink, but I'll put it again in green. And so this velocity vector is the magnitude, which is just v without the vector symbol on it, times the unit tangent vector. So we stripped off the magnitude from the vector itself and just put that as a constant out front called v, and then we just looked at the unit tangent vector. When we differentiate that, we use the product rule. So we got our product rule in the next line, And this comes from the second part of the product rule that says it's just the first function v times the derivative of the second. Okay, so that's where the first v is coming from. The next v we're going to get is actually hidden in here. It's hidden in the t prime. And the way we get it out is we say, well, t prime is the magnitude of t prime times the normal vector. That's coming from this fact back here, that the normal vector was defined to be the vector that had direction t prime, but normalized, so we divided by the magnitude of it. So just rearranging that, we get that t prime is the magnitude of t prime times n. And so that gives us that next line. And then what we do is we go to work on this piece, and we say, what is the magnitude of t prime? Well, that gets related to the curvature. The curvature is precisely the magnitude of t prime over r prime. And r prime is that other velocity, or that other speed component coming in. So this is the magnitude of r prime, but r prime is just another way of saying v, and that's the magnitude of the velocity vector, which is just v itself. So that's where it came. It came from over here. So that v and this v combined together to give us our v squared. So that's where our v squared came from. Good question. All right, so let's go ahead and derive these formulas. Why do the dot product and the cross product have any purpose cropping up here? Let's see. So the first thing we're going to do is we're going to start with what our acceleration vector is. So our acceleration vector is given by v prime t plus kappa v squared. So we've got this, and now what we're trying to do is we're trying to show that both of those scalars in front of those vectors can be obtained by taking these various dot products and cross products. Okay, so if I want to get access to this coefficient out here, if I want to get access to that, then what I'm going to do is I'm going to try to get rid of that n vector. I want to get rid of the normal vector. And the easiest way to do that is to just dot this whole expression with something that's normal to the normal vector. Something that will, when I dot it to n, gives me 0. But I already know that the normal vector is perpendicular to the tangent vector. And the tangent vector is in the direction of velocity. So what I'm going to do is I'm going to dot with the velocity vector. Dot this whole expression with the velocity vector. And that velocity vector is just the magnitude of it, v, times the tangent, unit tangent vector. So if we dot it with this, we get a dot v is equal to, and then we dot the other bits, so we get a v prime v t dot t plus, and the reason we're dotting it with the velocity vector is because that's in the tangential direction, which is perpendicular to the normal direction. So we get a 0 there when we dot t and n. So I'll just indicate here, because this is t dot n is 0. Okay, so then what's next? Well, t dot t is a unit vector, so that's 1. And because we get that that's 1, then what follows from this is the acceleration we can write as r double prime. The v we can write as r prime. So that's just a dot v, so that's that left-hand side. And then the other side becomes v prime and times v, but v is just the magnitude of r prime. So I'm just replacing what these v's and a's are in terms of the original expression that gives them, and that's our vector valued function r. And so that tells us then that v prime is equal to r double prime dot r prime all over the magnitude of r prime. And that's what we wanted to establish. That's our first formula. And you might object and say, well, wait a minute, the R double primes and the R primes are switched in the dot product. But that's fine, because dot product's commutative. It doesn't matter which order we dot them in, we're going to get the same result. So that's that first result established. Now I want to get the normal vector, or the normal component, sorry. So what is the normal component? Well, an is the curvature times v squared. That's what our formula tells us above. And now we're trying to say, well, we want to come up with a quick method for determining what k and v squared are. I say k sometimes, I say kappa some other times. It's the curvature is usually denoted by kappa, but sometimes I'm calling it k. So what is the way we can compute these things? Well, we can use the fact that we know the curvature is related to the cross product. And I'm just going to flip back to a previous lecture, 13.3. And here it is, our theorem 10, which tells us that curvature, kappa of t, is the cross product of r prime and r double prime over the magnitude of r prime all cubed. So we can use that result. So let's go ahead and throw that in here. This is r prime cross r double prime in magnitude all over r prime cubed. That's our curvature part. But then we're multiplying by v squared. But that's just the magnitude of r prime all squared. And so we get those squared, the two magnitude of r primes canceling with two of them on the bottom. And so we get r prime cross r double prime all over the magnitude of r prime. And that's the other formula we needed to establish. So we've got these two nice formulas, one dot, one cross. And now you can probably see why I wanted to write the r prime first in the dot product for the tangential acceleration, just because of the symmetry it gives with the normal one. I can't switch the order of r prime, and well, actually I could, because I'm taking the magnitude, so we could switch the order in the cross product. What would get introduced is a minus sign, but since we're taking the magnitude, that would disappear. But the idea here is I wanted to write down the formulas in such a way that there's only really one change that happens. The dot turns into a cross. And a magnitude has to get thrown in there because these things are supposed to be scalars. And the dot product already returns a scalar, but the cross product would return a vector, in which case we'd need to take its magnitude to get the scalar out. So those are our two formulas. Let's go ahead and do an example that shows how we can use them. So here we've got a space curve. We're imagining this is a position function for a particle traveling in space, and we'd like to find the tangential and normal components of the acceleration vector. So we're going to need a few things. So let's collect our ingredients together. We're going to need to know the derivative, r prime. So that's 1, 2t, 3. We're also going to need to know r double prime. That's 0, 2, 0. At some point, we're also going to need to know the magnitude of r prime, and that's going to be the square root of 1 plus 4t squared plus 9, or in other words, root 10 plus 4t squared. So the tangential component is given by r prime of t dot r double prime of t all over the magnitude of r prime of t. So we work out the dot product and we get 4t all over the magnitude, which is 10 plus 4t squared. So there's our tangential component of the acceleration. What do we need now? Now we need to work out the normal. The normal is given by r prime of t cross r double prime of t divided by the magnitude of r prime of t. So we're going to need to know the cross product. If you set these things up in the right way, the cross product, we normally have to write down the determinant with I, j, and k. But if you look up here, I've positioned my calculations of the two vectors and stack them in such a way that I can use this as my visual representation. I could think of this as, I, j, and k sitting up here, and then do my determinant calculation to get the cross product there. I'm just going to erase that. But the idea is I don't have to rewrite these things. If I've stacked them somewhere else in an appropriate way, I can just use that to visualize the cross product. So what is our cross product in this case? Well, we need to get the first component. I'll just write on this and then I'll erase. So we get the first component by ignoring that column and doing the product of the other two components. So 2t times 0 and then minus 2 times 3. So we get a minus 6 for our first component. And then for our second component, I'll cross out the middle one. Both zeros on the bottom mean that both products are going to be zeros, so we're going to get a value of 0. And then I will cross out that third column, and the remaining one is 1 times 2, which is 2, minus 0, so we get 2. And so there is my cross product. And again, we've got the 10 plus 4t squared on the bottom. And so the magnitude of this is the square root of 36 plus, that should have been 36 plus 4, or in other words, the square root of 40, all over the square root of 10 plus 4t squared. And so there's our normal acceleration component. And so that's how we can compute these tangential and normal accelerations using the original vector valued function r. We just use the corresponding dot products and cross products of their various derivatives. All right, so that's it for this section on velocity and acceleration for these space curves. Now what we're going to do is, as we've essentially now wrapped up the chapter 13 stuff. So we popped back and forth from 13 to 14 and then back to 13. So we've done now all of the vector valued function stuff that we want to do in the course. So we worked out space curves. How can we describe them? We describe them by these vector valued functions r of t. The derivative of it represents the tangent vector. We can find tangent lines. The second derivative, now we've made an interpretation in terms of acceleration. We've also got it related to the curvature as well. And so we got these various formulas for curvature and then velocity and acceleration for these space curves. Now what I want to do is I want to jump back into chapter 14 for multivariable functions again and continue on with the calculus of those. So we've already done, if we think about what we've done so far in chapter 14, we introduced functions f of x, y. We introduced what a partial derivative is, so the x derivative or the y derivative for that function. And then we worked out tangent planes, how to find the tangent plane. And the tangent plane is also referred to as a linear approximation for the function at the particular point. So we've done that so far. Now we're going to take a step further, and we're going to talk about derivatives a little bit more generally and how to compute derivatives using the chain rule if we've got compositions of things happening. So we're now going to do the multivariable chain rule. To do this, I'm going to motivate it with a problem that we would have seen in Calculus 1. So this is a problem we would have seen in Calculus 1. Falling sand forms a conical sand pile, where the sand pile has height 5 meters, base radius 2 meters, and its height is increasing at a particular rate, while at the same time its base is increasing at a particular rate. So the idea here is we've got sand that's being poured out of some spout, let's say. We got sand being fired on top of a pile. As it lands on the pile, it sort of rolls down the side. The base gets bigger and bigger and bigger, but so does the height as it builds up. And we'd like to know how the volume is changing, given that we know how the radius and the height are both changing. So that's our goal. So let's just indicate a few things in here. There's our radius. Here's our height. what we can do from these two bits of information is we can fill out what the volume is. The volume of a cone is 1/3 pi r squared times h. So that's the volume of a cone. It's basically 1/3 the volume of the corresponding cylinder you would get with a constant cross-sectional radius of r. So that's our volume of our cone. And what we have is that r and h are both functions of t. So this is where it becomes a calculus 1 problem. It's not that the volume is a function of these two variables. It's the fact that the function is, the volume function is actually a function of one variable, time. And the way we're getting at that is we're saying, well, the volume is 1/3 pi r squared h, but both r and h are functions of time. So you can see that this is just a related rates problem from calculus 1. So this is one we would have done in calculus 1. So how do we do it in calculus 1? Well, what we did was we said, well, we're interested in dv dt. So what is that? Well, the way I would get dv dt in terms of the things that I know this number here is 0.4. That's how the height is changing. So that's dh dt. So that's dh dt. And then I have this other number here. That's dr dt. So how do I get the change in the volume? Well, I have to relate it to the change in the radius and the change in the height. And I can do that through the product rule. So by the product rule here, I would get that it's 1/3 pi times the derivative of the first function, which is the r squared. So that I'll put a 2 up here. So that would be a 2r. And then what do we have here? So it's 1/3 pi times the derivative of the first function times the second. But the thing I have to keep in mind here is that when I take the derivative of the first function, I get an r squared. That's the inside function being squared, but r is a function of t. So I'm thinking of this as sort of a composition. It's the r of t function being squared. So the derivative of the r squared is 2 times r times dr dt. And then we multiply by the second function, which is h. So that's the product rule part of it. Plus 1/3 pi, the first function, r squared, times the derivative of the second function. That's dh dt. And so we're using the product rule here along with the chain rule, and this is our related rates type approach to these kinds of problems. Find a relationship between all the variables, then differentiate it. Now at the point r equals 2, h equals 5, dr dt equals 0.7, dh dt equals 0.4. We can plug all this information in, and we get that the rate of change in the volume is 2/3 pi times the r value times dr dt plus 1/3 pi the r value squared times dh dt. And so there's our resulting value. We could simplify that if we wanted to, but we don't need to spend time on this in the lecture now. This is just arithmetic. So what we've got here is that we've done our just a calculus 1 approach, right? We've done set up the relationship between volume and the variables, differentiate with respect to that independent variable time, use the product rule here because it was a product of two things, use a chain rule, and go through it. Now, what I want to illustrate with this example is that we can look at this through a new lens, through a calculus 3 lens. Let me see, shouldn't there be a 5 in the first part? Oh, yeah, I missed the 5, thank you. 5 here. Thanks for that. That was that h that was hiding on the other side of the derivative. So we can look at these things through a new lens, our multivariable calculus lens. And what we'll see, as this is going to be one of the first steps in the direction of, we'll see a lot of results that we took as sort of isolated results in Calculus 1 and 2. They turn out to be specific examples of more general results in Calculus 3. So if you wonder, how can people remember all the stuff from Calculus 1, all the stuff from Calculus 2, all the stuff from Calculus 3, and Calculus 4, and every other course you take in your undergraduate program, the idea is as you build up through your courses, you're going to learn more general methods, of which the stuff from before just becomes this particular example. And so there's no reason to remember the particular examples when you can get at them from a more general method. So that's sort of the step in the direction of this sort of higher level education you're going through, is the more you learn, in some sense, the less you have to remember, because the more you can derive. The more you understand, the more you can derive. So let's see what can we learn from our calculations here. Well, I'm just going to highlight a couple of things. The first thing I'm going to do is draw your attention to these two bits here. Look at the function v. How did I get those two bits? Well, this is just the partial derivative of v with respect to r. And this one is just the partial derivative of v with respect to h. So what we did was a product rule to get this, but when in fact, if we look at it from a higher order perspective, sort of a more informed perspective, we see that these are just partial derivatives. And that's no coincidence, because the product rule is actually a consequence of this more general result, which is known as the chain rule in multivariable calculus. And what the chain rule says is that if I have a function of two variables, f of x, y, and I think of each of those x's and y's as being functions of a third variable, t, then z is ultimately a function of that variable t. So it makes sense to ask, what is the derivative of z with respect to t? And it turns out that it's just the derivative of z with respect to x times the derivative of x with respect to t, plus the derivative of z with respect to y, plus the derivative of y with respect to t. So there's sort of a very nice sort of cadence or sort of rhythm here. It's like, what is dz dt? Dz dt is dz dx dx dt plus dz dy dy dt. And you just keep doing that for however many variables there are. If there was another variable w, it'd be plus dwd, or sorry, dz dw dw dt. You just keep going. We'll write that one down later on, but that's the idea. So that's our multivariable chain rule. I'm not going to prove it here. There is a proof, and you can refer to it in the textbook if you want. I just want to get right to using it. So let's do some examples. I've got this function z, which is arctan of x squared plus y squared. Both x and y are functions of t. I'd like to know what dz dt is. Notice the notation dz dt. D is used for derivatives of functions of a single variable. And that's what I'm really thinking of here. Z is a function of t, one variable. And that's because z is expressed in terms of both x and y. Both x and y are functions of t. So z is a function ultimately of a single variable t. So I can ask for its derivative, and the notation here is dz dt because it's a function of that one variable. So what is dz dt? By the chain rule, it's the partial of z with respect to x times dx dt plus the partial of z with respect to y dy dt. That's what our chain rule tells us, and so now we can go ahead and compute it. What's dz dx? That's the derivative of the arctan function. So that's 1 over 1 plus x squared plus y squared times the derivative of the inside, which is 2x. So that's our first bit. That's dz dx. And then we got to multiply by dx dt. Dx dt is 2t. Then I got to add to that the derivative with respect to y. So that's now 2y over 1 plus x squared plus y squared. Sorry, there was a squared there. I missed the square. So many squares happening here, and a square here. Why do I have that square there? Maybe I should have indicated. Recall that the derivative of arctan of x is 1 over 1 plus x squared. So that's the result I'm using here. And so in this case, our argument to the arctan is the x squared plus y squared. Okay, so then this is multiplied by the derivative of the y function, which is 3t squared. Okay, so then we can just put everything. So the idea here is this is a derivative of z with respect to t. So let's write everything in terms of t. So that x up top, that's just a t squared. I've also got another multiplied by 2t from that derivative of x with respect to t that's hanging out over there. And then on the bottom, I've got a 1 plus, and there's a t to the 4th plus a t to the 6th, all squared. And then we add that to the other part, which is a 2t cubed times 3t squared, all over 1 plus, I'm trying to get it in terms of t here, 1 plus t to the 4th plus t to the 6th, all squared. And so there's our final result. We can clean it up a little bit. We could put it over a common denominator, but the idea here is we've done the new part. We've done the derivative. The rest is just algebra. I do want to point out that this is a question that you could have very well done in Calculus 1. How could you have done it in Calculus 1? Well, the first step you could have done was just taken the t squared and plugged it into here, and taken the t cubed and plugged it into there. And now you've got z is arctan of t to the 4th plus t to the 6th, and then just done its derivative because it's a function of a single variable. So you could very well have got the same result using techniques from Calculus 1. Here, rather than plug them in first, we are exploiting structure. We're saying that, well, there is this outside function, arctan of x and y's, and there's these inside functions. X is a function of t and y is a function of t. So I don't need to plug them in. I can instead work with the derivatives of the outside functions and the derivative of the inside functions, which is, after all, what the chain rule is built to do. And so that's what we've done here. We've worked with the outside functions and the inside functions independently and pieced them together using the chain rule. So let's go ahead and look at the next example. This is just to see that this sort of pattern continues. I want to know what dw dt is. dwt is del w del x dx dt plus del w del y dy dt plus del w del z dz dt. That's by the chain rule. And you might say, well, the chain rule above only applied to 2 variables. But the idea is, yeah, it was written for 2 variables, but it actually works for arbitrarily any number of variables. You just keep going with the same pattern. Once you see how the pattern works for 2, it just continues for 3, 4, 5, and so on variables. And so then this becomes 2x over 1 plus x squared plus y squared plus z squared. That's the derivative of the first part, times dx dt, that's 2t, plus 2y over 1 plus x squared plus y squared plus z squared. Again, I forgot the square on the bottom. So many squares here. Times the derivative of y, which is 3t squared, and then plus the same thing with the z, 2z over 1 plus x squared plus y squared plus z squared squared times 4t cubed, and then express in terms of t, much like we did before. Then just write everything in terms of t. I'm just going to write it like this because it saves time. There's nothing new going on here. We've done the derivative, we've done the calculus part. Now the rest is just algebra. So that's our chain rule. So let's go ahead and see how our chain rule extends for more variables. So not more variables in the sense of we've got our function of, in this case, arctan of x, y, and z, more variables in the sense that all of these variables were functions of just one variable, t. What happens if x, y, and z are functions of other variables, u and v, for example? How do we get derivatives in that case? So that's this next step. The chain rule for several independent variables. So we're thinking of w as a function of x, y, z. And x, y, and z are actually functions of another variable, well, actually two in this case, u and v. So ultimately, w is a function of u and v. How do we get its derivatives? In this case, since it's a function of two variables, u and v, we're going to look for partial derivatives. What's its u derivative? What's its v derivative? And the same sort of thing happens, the same sort of pattern happens, that if I want to compute the derivative of w with respect to u, I just proceed through and say the derivative of w with respect to u, it's the derivative of the first variable x with respect, sorry, the derivative of w with respect to the first variable x, and then the derivative of that with respect to u. So it's dw dx, dx du. And then it's the derivative of the next variable, so dw dy, and the derivative of that with respect to u. So dw dy, dy du. And then dw dz, dz du. And so what we get is this, again, sort of nice pattern happening. And the same thing happens for the other variable, for the v variable. dw dv is dw dx, dx dv, dw dy, dy dv, dw dz, dz dv. So this nice pattern. The key to noting this pattern is that these variables are always the same. Those are our transition variables. We're trying to find the derivative of w with respect to u by transitioning through these intermediate variables x, y, and z. So I differentiate with respect to those ones first, and then the derivative of those with respect to the ending variable. So let's go ahead and look at this example. We want to find dw du. In this case, w is a function of two variables, u and v, so that's why I'm using the del notation here. So dw du, what is that? That's dw dx, because that's one of the variables that's w is written in terms of, dx du, plus dw dy, dy du. And that's the derivatives we're going to have to compute and piece together to get the final derivative. So what is dw dx? That's a 1 over 1 plus x over y all squared times the derivative of the inside function. There's a chain rule here for the arctan. We're finding its partial with respect to x, treating y as a constant. So it's derivative of the arctan, 1 over 1 plus whatever's inside squared, times the derivative of the inside function with respect to x. That's a 1 over y. That's our dw dx. Then we need to multiply by dx du. So that's multiplied by 2u. And then we have to do the same thing for the next one. 1 over 1 plus x over y all squared times the derivative of the inside. That's the x over y part. The derivative of that with respect to y. So that's negative x over y squared times the derivative of y with respect to u. That becomes a 2u. So doing the chain rule here for the multivariable functions, we've got to do partial derivatives, and with those partial derivatives, we'll have to use our regular old chain rule for one variable. So now we can put these things back in terms of u and v. So this is a 1 over 1 plus u squared plus v squared over u squared minus v squared, all squared, times 1 over u squared minus v squared times 2u, plus 1 over 1 plus u squared plus v squared over u squared minus v squared, all squared. Negative x is negative u squared plus v squared over y squared, u squared minus v squared, all squared, times 2u. And we could try simplifying, but I'm going to leave it here because it's the calculation that I'm interested in, not the simplification. Okay, so this is the cadence that we have. I'm just taking a peek at the chats. Where did the 1 over y come from? Good question. I'm differentiating. So this piece here is coming from the derivative of w with respect to x. So that's of arctan of x over y. And when I do that derivative, I've got to do a chain rule. The derivative of the outside function, the arctan, is this bit. And then the derivative of the inside function. So this is the derivative with respect to x of the inside function, x over y. So that's just our regular old chain rule from Calculus 1, where we're differentiating this arctan of x over y with respect to x. Y is a constant, so it's just a function of a single variable. That's where it's coming from. Okay, so those are our chain rules. Get the cadence. Yep. Question?
As if we face this kind of questions in midterms, can we keep in this form, or do we need to simplify it?
No, you'd keep it in this form. Yeah, don't bother simplifying unless you're asked to do something with it. Then never simplify.
Oh.
Yeah, never simplify. If it's just compute the derivative, leave it like this. For in terms of assessments, leave it like this. If you're then asked to do something with the derivative, better to have it in a simplified form to work with it. Otherwise, it's just more complicated to work with it in this form. But if it's just what is the answer, leave it in this form, because this shows me how you actually calculated it, which is what I'm interested in a question like that, not the final answer. Okay, so let's have a look at this next one. Suppose that we have a function f of u, v, x, and y, but both u and v are functions of x and y. So these themselves, u and v, are actually further, they're functions of x and y. So it might seem weird why we're doing this, but it'll make sense in the next example. But we can go through the process. Now I'd like to know what del w del x is. Well, del w del x. Let's just go through it. It would be derivative of w with respect to the first variable times that variable with respect to x plus the derivative of w with respect to the next variable, v, times the derivative of that with respect to x, plus the derivative of the next variable, w with respect to x, times the derivative of that variable with respect to x, plus the derivative of w with respect to x, with respect to the last variable, y, times the derivative of that variable with respect to x. Again, I'm going to put these in a different color. I'm just following the pattern. Right? These are my intermediate variables at each step along the way. So these ones have to match. The other variable, w and x, are the two variables that I'm interested in for my derivative because I want dw dx. So I just need to transition through those intermediate variables. And I just run right through all the variables for f, u, v, x, and y. At this point, we say, well, wait a minute. dx dx, that's just the derivative of x with respect to x. So that's 1. What about this? Well, we're thinking of y and x as our independent variables. So what's the derivative of y with respect to x? Well, that would be 0 because it's independent of x. And so this boils down to dw du du dx plus dw dv dv dx plus dw dx. And that's what our result ends up being. And I will say similar for dw dy. You just do the same thing. It's just that those last two will sort of change rules. Yep.
How is dy over dx independent?
So we're thinking of these are all independent variables in some sense, but then the further bit of information is that u and v are actually functions of x and y. It's like, okay, so u and v depend on x and y, but x and y are independent of each other. Whereas they're independent variables, we haven't been told that they're related to each other in any way, so we've got to assume they're independent. So if you want to think of it this way, suppose I had a function f of xy is equal to y, and I ask for the partial derivative, del f del x. What would the answer be?
0.
Exactly. So that's all I'm saying.
Oh, okay.
That's all that's saying there.
Oh, okay, okay. I get it now.
Perfect.
Thank you.
You're welcome. So let's see how we can use this result. And so the way we're going to use this, I'm just going to ask you to think, maybe concrete terms. Suppose I have an x squared plus y squared minus z squared equals 1 type function. I use function in the loosest sense of the term because this isn't a function of z in terms of x and y, because for any x and y value, there's possibly 2 z values. So it's not a function as in input-output. So this is more a surface. So how can I do things like find tangent planes to surfaces and the like? Well, the idea is to say, well, I'd like to think of z as a function of x and y if I can, but it's now an implicit function of x and y. And so I'd like to do some sort of implicit differentiation like I did in Calculus 1. How can I do that here? Well, we can do that in using the chain rule, much as we did with Calculus 1. We're now just extending these ideas using our new chain rule. And the idea is as follows. We think of our expression of the form some function of x, y, and z. And here, z is a function of x and y. So it's much like that last example where I had u, v, x, and y, but u and v were functions of x and y. Here I've got x, y, and z, where z is a function of x and y. And so I can do things like, okay, what is our derivative in this case? So I'm going to start with f of x, y, z equals 0. And I want to find the derivatives with respect to x and y. So what's the derivative of z with respect to x? What's the derivative of z with respect to y? Well, the way we do that is we just go ahead, so I'll say the first case, we just differentiate through. Let's find the derivative with respect to z. And in order to do that, we have to do the chain rule. So it's the derivative of f with respect to x times the derivative of x with respect to z plus the derivative of f with respect to y times the derivative of y with respect to z plus the derivative of f with respect to z times the derivative of z with respect to sorry, why am I differentiating with respect to z? Trying to go too fast, not thinking, I guess. We want to differentiate with respect to x. I'll change these ones to x because this is really our only change here. There we go. So what is our derivative with respect to x? It's the derivative of f with respect to x times x with respect to x. Then the derivative of f with respect to y times the derivative of y with respect to x. Then the derivative of f with respect to z times the derivative of z with respect to x, right? I'm just proceeding through all of the variables and just differentiating them accordingly. And the derivative of the right-hand side is still 0. This is 1, this is 0, and so we can solve for dz dx, and that is negative f sub x over f sub z. And so that tells us how we can find the derivative of a surface which is defined implicitly in this way. So an implicit function, z is implicitly defined in terms of x and y. We just take the derivative of x, the expression with respect to x, and divide by the derivative with respect to z. And we can do the same thing for for y. That's what this next part says. Do the same thing for y. It's just negative fy over fz. So next day we'll do the two problems which show us how we can use this implicit partial differentiation to do some examples. And then we'll move on to the next section. So I'm just going to stop the recording here.